the 3D computational fluid dynamics problem for
Hello
steady state
everyone,
and
today we're
unsteady
going to
state
talk
problem.
about
The contents of the lecture will be as follows. First, we'll talk about the importance of the computational fluid dynamics problem, then the Navier-Stokes equation, the penalty formulation as a solution method. Then the lecture will be divided in two parts. First, the steady state part for 3D problems. Here we will solve the problem using two techniques. First, as a single domain, use the method fundamental solution. Second, the problem is solved as a multi-domain using the method fundamental solution. We'll see how to treat the domain integrals and the solution procedure. Then we will apply this formulation, the proposed formulation for the lead-driven cavity example for the two cases, single domain and multi-domain. The second part of the lecture will be the unsteady state problem for 3D. We will use the method fundamental solution to solve the problem as a single domain. Then we will talk about the importance of the solution, the derived fundamental solution, and how to treat the domain integrals, and has many applications. There is a flow around buildings, application in airplanes, biomechanics, climate problems, weather forecasting, and many other examples. The Navier-Stokes equation for viscous incompressible flow will have two equations: the mass conservation equation or the continuity equation, and the equation of momentum, which will be written in dimensionless form as follows. This is the pressure gradient, the viscous term, the convective term, which is a non-linear term, the inertia term, which will be zero in the steady state case. The penalty formulation, in the penalty formulation, we eliminate the pressure term, assuming this relation. Or to satisfy the continuity equation, lambda must be very large, approaches infinity, so that the pressure term is finite. Substituting in the momentum equation, the Navier-Stokes equation will be as follows, which is analog to the Navier equation of elasticity as seen here, with the following. The velocity in Navier equation will be the displacement in Navier equation. The convective term will be negative, the domain load. The inverse of Reynolds number will be the shear modulus. The first part of parameter will be lambda will be part. Here we will solve the problem as a single domain using the meshless method fundamental solution. The idea of this technique is that we assume that we will let the real problem be embedded in infinite domain. So to make this virtual problem be as the real problem, we put source points with unknown forces, so as to make the boundary conditions of the virtual problem be the same as the boundary conditions of the real problem. We here take the advantage that we know the solution of the problem in infinite domain due to unit load, which is the fundamental solution. So we can obtain the displacement at any point using the method of superposition from all the source points distributed on the fictitious boundary as shown in this drawing. So the displacement at any part can be computed from this equation, and also the traction can be computed from this equation, where phi is the load, is the fictitious load as the source point, and u asterisk is the fundamental solution, and t asterisk is the fundamental solution for traction. The second part is the part due to the domain load, where b is the domain term, which will be here the convective term. Now it seems that the method is meshless. We don't need any discretization except for that the integral term, which will the second term, which we will see here how to make this integration also meshless, so that the problem will be totally meshless without any discretization on the boundary or in the inner of the domain. Now using these two equations, we can make a system of equations to solve the problem. The system equation will be as follows. This vector is a vector of the prescribed values on the boundary. U bar is the prescribed displacement, T bar is the prescribed traction, N1 and N2 are the number of points for the prescribed displacement and prescribed traction. This is the vector, the matrix, the influence matrix containing the fundamental solution. Phi is a vector of the unknown values at the source point. BP is the domain integral or the particle solution as seen in the previous equations. To compute the convective term at each stage, we need to compute the displacement, the derivative of the displacement, which from the equation of the displacement we can compute the derivative of displacement as follows. It must be known that this matrix and this vector is known from the beginning of the problem, so we can store it as the beginning of our solution. We need not compute at each stage. So we compute also only the vector of the phi and the vector of the particular solution. Also, in case of the derivative, we'll deal it using the derivative of the fundamental solution is known technique where we distribute from the beginning of the points inside compute the phi. We domain of the problem, and we can store the value of the integrand, this derivative from the beginning of the problem, and compute only the derivative of the functions as the case of the radial basis function. Now, how to deal with the integral? So here the problem is totally meshless, and the integral need any visualization on the boundary or equations inside domain. The solution procedure will be as follows. First, we compute the known matrices and store it. Then we start the nonlinear loop where we will solve the system of equations. At the beginning of the solution, we assume the convective term to be 0, and at each time at each stage we compute the new convective term. We compute phi. From it, we can compute the internal points, the internal velocity, and its derivative. Then we can compute the convective term, where K is the relaxation parameter used to stabilize the solution. Then we can make the difference in the results between the current step and the previous step for the velocity. If a tolerance, if a prescribed tolerance is satisfied, the solution is complete. If not, we start the loop again and continue until the tolerance is obtained. Here we solve the well-known problem, which is the lead-driven cavity, which is its cube with dimension 1 and the prescribed velocity in y direction equal 1. We'll solve it for Reynolds number 100 and Reynolds number 10. As the relaxation parameter taken is 0.05, in order for the parameter lambda to be large enough, the Poisson ratio must approach zero point 0.5. So we'll take it 0.49999. Here we solve the problem for Reynolds number 10. The Monte Carlo points will be 10 at each direction. The source offset will be 100% of the distance between the points on the boundary of the problem. We solve it using 10 by 10 boundary point at each face, and 30 by 30 and 40 by 40. Here is the reference that we will compare with. This is a solution for the case of 40 by 40, which give good agreement with the result of the paper. Here we solve the for Reynolds number 10 with point distribution 40 by 40 boundary point per face, and the Monte Carlo points will be 14 in each direction with source offset 300. Here is the reference that we compare with. Now the second part will solve the problem as a multi-domain problem, where the real problem will be discretized into two domains. The advantage here is that the obtained matrix is a sparse matrix, not fully populated as the case of the single domain. Each subdomain will be solved using the massive fundamental solution as here in the drawing. So we can write the same equations written before for displacement interaction for each subdomain. We will rearrange this equation to form an equivalent stiffness. So from we can get phi with respect to the displacement and substitute in the traction equation, so we can find the equivalent stiffness. And we will use instead of the traction, we use force. So we will multiply the traction by the area between the points. equation will be as follows. This is a force vector, the equivalent stiffness which can be computed from here. L is a diagonal matrix where each term in the diagonal is the area between the points. UP and FP are the particular solution for the displacement, a particular solution for the force, which is computed from the domain integrals. We will assemble these equations for the all the subdomains. So this will be the assembled equation where n and u represent the known part and unknown part of the force and displacement. Rearrange these equations to make knowns and unknowns. So here this is the unknown vector and this is the known vector. It must be clear that this matrix and this matrix is constant all over the problem, so we can store it from the beginning of the solution. And also this vector, the vectors will be changed, that will change at every stage, is the unknown vector here and the vector of the particular solution, which represents the convective term here. The solution procedure will be the same as the previous case. So we'll talk about the problems. We'll solve here the same problem as previously. Here we make the problem two domains, two vertical domain and two horizontal domains. For the case of the Reynolds number 100, we will distribute the points 20 by 20 points per face of the problem and 24 points in each direction for the Monte Carlo. The source offset for the vertical will be 0.15. The distance will be 0.15 for the outer faces and 0.125 for the inner faces. And for the horizontal subdomains will be 0.21 for all the faces. This is the results compared to the reference. In case of Reynolds number 100, we use the same distribution. This is the reference. This is the result for the Reynolds number 100. The second part, the difference here between about this problem and the state problem is the appearance of the inertia term problems for 3D. So we see how to deal with this term. We'll discretize, we'll approximate the inertia term into known and unknown part. Known part, which is the displacement at time t plus delta t, and the unknown part, which is the displacement at three previous steps, t minus delta t and t minus 2 delta t. So using this approximation, we can add the unknown part to the differential operator, and the known part will be left with the convective term in the right hand side. So the equation, the new differential equation here is a steady state like differential equation. The difference here is that the differential operator is new, so we need to obtain a new fundamental solution. We cannot use the same fundamental solution. And the domain term is not only the convective term as previously, but the convective term plus the known part of the inertia term. So the same procedure used for the steady state, we can use it here for this case. So using the Mills fundamental solution, we'll solve here the problem as a single domain. The same equations is written. The only difference is that the domain term is the addition of the convective term and the known part of the inertia term. These two parts are known at each stage, so we only compute phi. We can store from the beginning the fundamental solution of the displacement and traction from the beginning of the problem, as the case of the steady state. Now how to obtain the fundamental solution for the new differential operator. We solve this differential equation using Ormander method or Cayley-Hamilton method. So we obtain here the new the fundamental solution for the new differential operator. We will treat here the domain integrals as the same for the steady state case using the Monte Carlo integration technique. So the problem will be purely meshless. The solution procedure will be as follows. First, compute the matrices, the known matrices. Then we begin the loop at each time step. So at the current time step, we will compute the known inertia term from the three previous time steps. Then we will enter the nonlinear loop, the loop for the convective term. We will compute, solve the equation, this equation, to compute phi. Then from phi we can the internal velocity and the derivative, from which we'll compute the convective term. Then we'll compute the difference between the velocity at the current step and the previous step of the nonlinear term. If it prescribed tolerance is obtained, then we will compute the we will return the next time step. If the tolerance is not obtained, we will loop another time on the convective term. Thank you for your kind attention.